that we're talking about solutions of systems of linear inequality on a plane. So let me add that, on a plane. By that, I mean not solutions of linear inequalities as you've seen it before along the real number line. This is not what we're talking about. We're talking about one or more inequalities where they have a solution on a plane, not along the real number line. That's the critical jump that you have to make in your mind about what we're going to discuss right now. So all these solutions are talking about solutions on a plane, not along the real number line. So a real number line would be solutions in one dimension, but when we talk about plane, we're talking about solutions in a two-dimensional space. Okay, having said that, let's first identify the kind of language that would translate into an inequality. And that would be language such as at most, no more, and at least, and so on. So this kind of language suggests not an equality, but an inequality. Okay, so language such as this translates into inequality, right? We've been talking about translating things from plain English into symbolic mathematical form, and this is a way to, this is one of these types of phrases are clues that we're going to create inequalities. Okay, so let's begin, as usual, with simple examples and then build up on that. Suppose we want to show the solution of this. So show the solution of this inequality on a plane, right? If you were to show the solution of this along the real number line, it would be just that, right? It would be something like bracket that goes through 0, including the 0, and all the way to positive infinity. But that's not what we're talking about here. We're talking about the solution of this on a plane. So how does that work then? Okay, it works like this. So first we want to draw the axis for the plane, for the two-dimensional space. Then x equal to 0 would be the boundary line. So this is very, very critical. First, we must find the boundary line. The boundary line is when the equality equals some value, in this case 0. So x equals 0 is the boundary line, right? Let's find where that line is. X equals 0 means the y-axis. So let me use my thick marker here, or maybe I should use my red marker here, red ink. So that is x equals 0. All of that axis. The y-axis, the equation of the y-axis is x equals 0, right? And that's the boundary line. Because on this line, x value is always 0. It's not going to be negative. It's not going to be positive. So this is saying anything equal to or greater than that boundary line. So including the boundary line, then the solution of this on a plane is all of this space. Like that. And we could go off the page and off this whole campus by extending this vertical y-axis into positive and negative infinity. But we're not going to do that, right? You can see the point from that. Okay, so there's infinitely many solutions for that. On the other side of the plane, starting from this, from this boundary line. Okay, so let's make this a little bit more interesting by saying, show the solution of x greater than 2 on a plane once again, right? So let me, the on a plane part should be implied, but because we're just introducing this concept, I want to write it a couple of times, then I'll stop writing it. But in this class, we are not talking about the solution along a real number line. We're just talking about all these solutions on a plane. So I'll do it one more time and then I'll stop. Okay, so once again, we want to draw the axes, x and y. And 2 would be, let's say, somewhere here, right? Somewhere there. But notice that this time, x should be greater than 2. It cannot be equal to 2. Therefore, the x equals 2 boundary line cannot be solid. It cannot be solid line like that. We show that as a dashed line. So dashed because the dashed line is not part of the solution of this inequality. Only any value of x that is greater than 2 can be part of that solution. So having said that, then we can lightly shade this region, right? And this time, notice the boundary line is dashed because this equality is a strict inequality without the equality symbol underneath it, right? Unlike this one. This one is greater than or equal to, so we had the solid line. Here we have just greater than 2 and it has to be a dashed line. Okay. So let's make our examples a little more interesting, just a bit. This time, so far, I'm sure you've noticed that even though we were finding the solution of these inequalities on a plane, the y variable was missing, which is fine. But now let's bring in the y variable. So we want to show or solve x plus 2y greater than 4. So notice that now we have 2 variables, which is great. Now there is no mistaking that we're talking about the plane, right? Because of the xy. But in the previous 2 examples, because one of the variables was missing, people might think we're talking about solving those inequalities on a line, whereas no. In those cases, as well as this one, we're talking about solutions of these inequalities on a plane. Okay, so just like those simpler examples, our objective here is to find the boundary line first. How do we find the boundary line? Well, we're going to rewrite this as an equality. So x plus 2y equals 4. We're going to find that boundary line. There we're going to test on which side is the solution. How do we find the boundary line? You can use any, for example, you can give x any value and calculate at least a couple of points and then plot those 2 points and draw a straight line through them. But the easiest points to pick are the intercepts, because one component is always 0, right? So I'm going to use the x and y intercepts rather than any point, because it's simply because it's easier. So if x equals 0, which means we're looking for the y-intercept, then y would be equal to 2, right? That's easy to see, because if we plug in for x with 0, then you get 2y equals 4, and then y would be equal to 4 divided by 2, which is 2. So the y-intercept is 0, 2. So let's find the x-intercept, which means y equals 0. If y equals 0, plug for y with 0, then x equals 4, which means the x-intercept is 4, 0. Okay, so let's plot these 2 points. I'm going to dedicate this part of the page to that. So these are our axes. So that's y, this is x. And these are nice, easy, small numbers. So I'm going to make my increments a little bit large. 1, 2, 3, 4. And then 1, 2, 3, 4. Right? So one of the points, the y-intercept is 0, 2. That's that. 4, 0 is that. Right? 4, 0 and 0, 2. And now we can simply draw a line right through those 2 points. That will be the boundary line. Now, should I draw a solid line or a dashed line? Have you thought about that? Give it a thought. Should it be solid or dashed? It should be dashed, right? Because the equality underneath this is missing. This is a strict inequality, so this side should be greater than 4. It cannot be equal to 4. So we're going to draw a dashed line. Like that. So that's our boundary line, but it's not the solution yet, because the solution has to be greater, this side has to be greater than 4. So either this side is the solution or this side. How do we know which side? Well, we pick a test point. So testing, and the test points can be anything. Testing, the easiest one would be the origin. Testing 0, 0 in this inequality. Testing 0.0, 0 in this inequality. And if it's valid, then this side is the solution, the same side as the test point. If this test point does not check out in this inequality, if we don't get the 2 sides to make sense in this inequality after we plug this point in there, then the opposite side of the test point, which is that point, is the solution. So let's find out which one is which. So I'm going to substitute this 0, 0 in there. We're going to have 0 plus 2 times 0 greater than 4, 0 plus 0 greater than 4. Check this out. This is saying 0 greater than 4. Is this correct? Definitely not. So we picked the test point on this side, and it didn't check out in the original inequality. That means the opposite side of this boundary line is the solution. So our solution is that side. Okay, because the test point, which is on this side, this is 0, 0. We plugged it in, and it did not make sense. So the opposite side of that line should be the solution. Okay, let's do another example. Suppose this time we want to find the solution of this system of inequalities. 6x plus 3y less than or equal to 6, x minus 3y greater than or equal to 1. Okay, just like before, we have to find the boundary line for each one of these inequalities and then see where the individual solutions overlap. The previous example, this one, it was just one inequality. So that's all we looked for. But this is two inequalities, right? Because we have two, we have to find the solution of this one, find the solution of the second one, and then see where those individual solutions overlap. The overlapping piece is the solution of the whole system. Okay, so let's do that. First we're going to find the boundary lines. So for this one, 6x plus 3y equals to 6, right? Because we're finding the boundary. Okay, as usual, as before, I'm going to use the x and y intercepts to find the boundary line. So if x equals 0, what do we get? We get 3y equals 6. That means y equals 6 divided by 3, 2. That means the y-intercept is 0, 2. If y equals to 0, then we have 6x, right, equals 6, because with y equals 0, that term drops out. So with that, we get x equals 1, or 1, 0 is the x-intercept for that line. So let's draw that line. And then we'll draw this one. Like that. So that is the x-axis, and then the y. These are small, easy numbers. So I'm going to make my increments a little bit large. So 1 and 2, and then 1 and 2. All right, like that. So 0, 2 would be that one, and 1, 0 would be that one. Let's draw a line through them. Should it be dashed or solid? Can you answer that on your own? What should this line be, dashed or solid? It should be solid because of the equality that we see underneath it. So the line, the boundary line itself can be part of the solution. That's the meaning of that equality under the inequality. So I'm going to draw a solid line through those 2 points. Some of these graphs tend to get a little bit crowded. Not all of them, some. So I'm going to write down next to this line the inequality that it's associated with. So 6x plus 3y less than or equal to 6, right? Okay, so let's find the solution of this, this inequality, which means we have to pick a test point. This line is not going through the origin, so that means we can easily test the origin for that. Test the origin in that inequality. We will have 0, 6 times 0 plus 3 times 0 less than or equal to 6. 0 plus 0 less than or equal to 6. Is that statement true? Absolutely. This mathematical statement is true. We picked a test point on this side of the line, and we ended up with a true mathematical statement. So the same side as the test point, which is that side, is the solution of that inequality, this one. So let's find the other line and find the solution of that and see where the solutions overlap. So this time we're looking for this boundary line. X minus 3y equals to 1, right? equals because we're looking for the boundary. As before, we're going to use the x-intercept only because, or intercepts in general, because it's easier. If you don't want to use zeros, you can pick x equals 1 and find y, and then set y equal to 5 and find x. But I think this is quicker and easier. So if x equals 0 here, what do we get? We get negative 3y equals 1, y equals minus 1/3, which means the y-intercept is 0, negative 1/3. If y equals 0, then we have x equals 1, so 1, 0 is the x-intercept. Let's plot these 2 points here and find the solution of that second inequality, that one. So 0, negative 3, that would be if this is 1, then negative 1/3, this point would be roughly here, and 1, 0 would be that. Once again, we can draw a solid line, right, because of this equality under that. Like that. And I'm going to write down the inequality on top of that line. That line is associated boundary line for this inequality. But now we have to find which side of that boundary line is the solution of this inequality. Well, we're going to pick a test point as before. So testing, that line is not going through the origin, which means we can pick 0, 0 as the test point and plug it into that inequality. If we do that, we get 0 minus 3 times 0 greater than or equal to 1. 0 greater than or equal to 1. Is this true? Is this a true mathematical statement that we ended up after picking the test point 0, 0? Is that true? No. This is false. This cannot be true. 0 is not equal or greater than 1. So we picked the test point on this side of the line, and it did not check out. That means the opposite side, this side, is the solution for that inequality. So where do these two solutions overlap? Right? When you look at the graph, they overlap in these regions. They overlap from here to here. Between these two lines, we have a solution. We have an overlap between that one. See those arrows that I had? And these arrows, right? They overlap here. So this region is the solution of the whole system. And I'm going to make it darker. Okay, that's our solution for this one. Okay, so that's the answer for that. I would imagine at this point you have questions about this, so please post them right underneath the video on the discussion board. Okay, so let's see another example. Suppose now we want to solve this system of linear inequalities. We have x plus y greater than or equal to 2, 2x plus y greater than or equal to 3, x greater than or equal to 0, y greater than or equal to 0. So here, the significance of these last two small inequalities is that we want to keep everything positive. See, let me bring this back. On the previous slide, notice that the solution of this inequality didn't have such a condition. So our solution of the system was on the positive side as well as the negative side, right? At least with respect to the x-axis. We have the part of the solution is here, which is on the positive side of the x-axis. Part of it is on the negative side of the x-axis. But in that one, we can't have that. The solution is limited only to positive sides of the x and y-axis. Okay, just like before, we want to find the boundary solution, pick a test point, find the solution for each of these, and then see where they all overlap. And that'll be the solution of the system. So first, I'm going to start with x plus y equals to 2, right? We're looking for the boundary line. So I'm going to pick a test point, the intercepts to find this line. So if x equals to 0, then y equals to 2, right? So we have 0, 2 as the y-intercept. If y equals to 0, then x equals to 2. Therefore, 2, 0 is the point, the x-intercept. So let's find that boundary line. I'm going to draw it here. Because we already know that everything is going to be positive, I'm going to give most of this blank space to the positive side. So this is what I'm talking about. See, instead of drawing my y-axis in the middle, I'm going to draw it way along this edge. Why? Because I know everything is going to be positive. So that would be here. Like that. Okay, so we have that. These are, once again, easy small numbers to work with. So I'm going to make them large. I guess that would be 1, 2, 3, and then 1, 2, and 3. That's all we need, up to 3. Okay, 0, 2 would be that point, right? The y-intercept. And 2, 0 would be this spot. And we can draw a line right through those. Should the line be solid or dashed? It should definitely be solid, right? Because of the equality that we see under the inequalities. So I'm going to draw that. Like that. And I'm going to write on top of this x plus y greater than or equal to 2. But we don't know which side of this is the solution until we pick a test point and go through that, right? So testing 0, 0, because this line isn't going through the origin, so we can still pick the 0, 0 as the test point. If this line did go through the origin, then we should pick another test point, because testing the origin would not give us any more new information, because it would be on top of the line, right? We don't want to know about the line. We know where the line is. We want to know which side of the line is the solution. So in this case, though, it helps us, the origin helps us establish that. So 0 plus 0 greater than or equal to 2, 0 greater than or equal to 2. Does that make sense? Absolutely not. So the side where the test point is located, which is this side, is not the solution, because it did not check out in the inequality. So the other side must be the solution. That side. That side is the solution, right? So let's find the other boundary line, which is associated with this inequality. So we have 2x plus y equals to 3. I'm going to have to move it up so you can see. All right, so let's find the boundary line using the intercepts, just like what we did here. So if x equals 0, then y equals 3. So 0, 3 is the intercept. If y equals 0, then we have 2x equals 3, which means x equals 3/2, which means 3/2 comma 0 is the x-intercept. So let's plot these 2 points on our graph. Okay, we have 0 comma 3 here, so that would be way up here in here. That's 0 comma 3, way up there. That's the y-intercept. And then 3/2 comma 0. 3/2 is 1.5, right? So it'll be right here, 3/2 comma 0. And let's connect those 2 points with a solid line. Like that. This, and I'm going to write down the inequality that is associated with this line right near it, so I don't get confused about which line is which, like that. But we're not done yet, right? Because we need to find a test point and see which side of this line is the solution of this inequality. So let's pick, once again, this line isn't going through the origin, so let's testing 0 comma 0, plug it in there. What do we get? We get 2 times 0 plus 0 greater than or equal to 3, 0 greater than or equal to 3. Once again, the test point it does not check out. So this side of the line, which is the same side where we picked our test point, is not the solution. The opposite side is the solution. That means this side of the line is the solution. Okay, so now where do these individual solutions overlap? Not to be forgotten that we have these two, right? These two are telling us to keep everything positive. That means the solution have to be on the positive side, on that side of the y-axis, and above the x-axis. That's what these two mean. So where do all of these things overlap? Well, they overlap in this region here, right? And at that point, we have a shift here. We have a point here. And then I can't go this way because there's no overlap here. Overlap happens to the right of this line because from here we have that going on, right? And then I can't dip below this x-axis because of y has to be greater than or equal to 0. So I can't dip below. So I have to go this way. So the final solution of this system is that. Right? Above the, I'm staying above the x-axis and to the right of the y-axis. All of that is the solution of this system. Okay, so this is all this example was asking for us to do. But I want to make a connection between this material and the upcoming material in section 4.2, which is using the geometric approach to optimize functions. We will get to that. So in section 4.2, we would go one step further by finding the coordinates of the corner points of the solutions region. So in this case, we have the coordinates of that point. It's 0, 3. We already know that. That's 0, 3. We know this one. That's 2, 0. But we don't know this one. In section 4.2, we have to find the coordinate of that. So why not start from now? So let's see how we can find the coordinates of that point. We're going to do it in a bit, next section, right? Well, we can find the coordinates of that system by solving a system of two equations. Why? Because the boundary lines Where is that point located? It's located at the intersection of this line and this line, right? That's the point of intersection. So if we set up a system and solve for those two lines, we're going to be able to find the x and y for that point. Those two lines, I'm sure you remember, are these two lines, right? So let me write them down here, and we'll figure out what is the coordinates of that intersection point. Again, this is helpful for the upcoming section. So the system we need to solve would be x plus y equals to 2, because we're looking for the coordinates of that point, the intersection point of this line and this boundary line. Okay, so we need to find the solution of that system. Okay, so we've solved these systems before. They're easy. These are really easy numbers. All we have to do is eliminate one of the variables, solve for the other variable, then plug back into one of these original equations and solve for the other variable that we eliminated. So y or x are just as easy to eliminate. I'm going to multiply the top equation by -1, and we're going to get negative x, negative y equals -2, right? Distribute this to both sides, including the 2. 2x plus y equals to 3. Let's add those two. The y terms drop out. We get minus x plus 2x gives us positive x equals minus 2 plus 3 is positive 1. So we found what x equals to. How do we find what y equals to? So simply plug for x with 1 in either this equation or that equation. Normally we'd like to pick the easiest one, right? So using the easiest equation, which is x plus y equals to 2, then let's plug in with for x with 1. 1 plus y equals to 2. So then y equals 2 minus 1, y equals 1. So now we have y. So combine these two coordinates together. We have 1, 1 as the coordinates of that intersection point. So we can come back here and say the coordinates of that point is 1, 1. Okay, I just wanted to mention that in preparation for what's coming up in section 4.2. Thank you for persisting through each of these videos with me, and I hope that this was easy to follow. If you have questions, please bring them up on the discussion board underneath each video, and I wish you a very good, safe day, and see you next time.